Yeah, welcome everybody to the next webinar during the Omicron Lab webinar week. So today we are looking into passive component analysis. My name is Bernhard and with me is...
Hello, I'm Florian.
And together we're going to give you a roughly an hour presentation on passive component analysis. But before we do so, we will have a few hints. First of all, so that you know, the webinar is being recorded. So this is so that we can afterwards send you a streaming link or a link to a YouTube video so that you can have a look at the webinar later on if you like. We are also offering the possibility that you ask questions. However, to experiences from the past, we have limited this to chat questions. Please feel free to send chat questions to us. So I have a second computer running. It's logged in under my name, Bernhard Baumgartner. And there you can send questions to me in the chat, and we will then address them during the webinar. Don't worry, we will not mention your name. We'll just read the question, and then we'll try to answer it. And if we don't manage to answer it during the webinar, we will take a note and come back to you via email. Okay, that's it so far. So let's have a look at what we have on the plate for today. So first of all, we are taking a look into the question, why do we analyze passive components? We will have a look on how to measure component impedances, and we will have a detailed look at the capacitor. Further on, we will have a look at an inductor and a flyback transformer, a transformer for a flyback. And finally, we'll have a look at filter simulation and compare it with some real-world results. And for sure, we will summarize our findings. So that's the plan for today. And I'm already handing over to Florian for the first theoretical part.
Yeah, when we are talking about passive components, we are talking about essential parts, especially in analog circuits, of course. And these parts are mostly used to either store energy or, in another point of view, to create filters that are frequency dependent, so that you can build a low pass or a high pass filter or whatever. A quick review on the inductor and the inductor equations. We know that the voltage on the inductor depends on the current slope, so the IDT, and the reactance of the inductance is also depending on the frequency, and that's omega L, or 2 times pi times the inductance. The impedance of the inductor is in this case only the reactive part, and that's J omega L, where J is the complex number, omega is 2 times pi times F, and L the inductance. For the capacitor, we have the same thing, but with a capacitance, and current and voltage are exchanged. And in this case, the impedance is 1 over omega C, or 1 over J omega C. So the capacitor lowers the impedance magnitude with frequency, whereas on the inductor, impedance magnitude rises with frequency. Back in school times, we always learned capacitor is a short circuit for high frequency. Well, that's of course very simplified, but still it explains the
basic behavior.
Yeah. So low frequency, high impedance, high frequency, low impedance. We will see that later in the measurements. Yeah, that was the theory, but in reality is different. So in theory, inductors and capacitors are purely reactive elements. There is no resistive behavior, and therefore they are lossless. However, we know that in reality there are the so-called parasitics that can strongly influence the real behavior, especially at higher frequencies. As an example, an inductor is created by winding a wire around the core, and this wire certainly has a non-zero resistance, so it shows some loss already. Then the winding itself forms an electric field besides the magnetic field that it should form. There is a potential difference on the wire, and this difference creates an electric field, and that's visible as a capacitance from outside. And the core is not lossless, so there will be core losses in the core. Also for the capacitor, we have plates or foils that are resistive, of course. They're rolled or stacked or whatever, and they create inductance by the current flow, and the isolator or the electrolyte is not lossless. So people use equivalent circuits to model the real behavior of the components, to have an approximation of the real behavior, and the very basic model, or the simplest model, that's the first order model, where we have one reactive element and one resistive element that models the losses. As an example, we can let the Bode analyzer suite measure an impedance and calculate the first order equivalent circuit directly. In this case, we measured a 5 ohm surface mount resistor and 1 megahertz, and the equivalent circuit in this case is an inductor with 4 nanohenries in series to a 5 ohm resistor. If we do that over frequency, then we can create a frequency sweep. The Bode analyzer suite offers you to select RS as series resistance, LS for series inductance, and CS, or also the parallel equivalent. And certainly they can depend on frequency, as we see later on. If you want to have models that are not only valid for one single frequency, but also for a certain frequency range, then you can use higher order equivalent circuits. We did now call these two examples the second order equivalents, because they have two storage elements inside, and in this case also two resistors to model different losses. So R1 in this case would model the loss of the isolator, and R2 would model the loss of the conducting path. And on the right hand side, an inductor with a parallel equivalent circuit, where we have an RS that models the loss of the wire, and an RT that models the loss of the core. And these two equivalent circuits are resonating circuits, so they have two storage elements. On the left hand side we can have a series resonance, and on the right hand side a parallel resonance. There are also higher order models, so you can go up in order how you want and can have better approximation. However, it gets more and more difficult to identify all the parameters. We have an application note on how to derive the equivalent circuit of a quartz that has 3 storage elements, and you can find it online on our webpage. The link is here in the presentation. You will receive the presentation later on, and so you don't need to remember that now. The parameter identification can either be done manually by doing certain steps, so measuring the series resonance, the parallel resonance, measuring an inductance, calculate capacitance from resonance and inductance, things like that. Or you use a curve fitting procedure, and there are also several different methods how to fit models to measurement data. But first we need the measurement data. So how can you measure impedance with the Bode 100? There are some direct impedance measurement methods. That means the Bode analyzer suite will directly display impedance values for you. You can either do the one-port reflection method or the impedance adapter, where we have impedance test fixtures for surface mount and through-hole type components. And we have the external bridge method, where you can build your own measurement bridge that is sensitive to a special application. Then there is indirect measurement via the gain measurement. So the Bode displays a gain, and you can derive impedance from that. Either the shunt through method, that's a 2-port technique, or the series through method, or the voltage current gain. And voltage current gain means that you apply a voltage signal to the channel 2 of the Bode 100 and a current signal to the channel 1 of the Bode 100, and the Bode will form channel 2 over channel 1, so that's voltage over current that equals impedance. So it will display a gain, but you as a user know this is impedance. Again, a little bit more in detail, the one-port method. The device on the test needs to be connected directly to the output of the Bode 100, and we recommend this method for impedance values from approximately half an ohm to 10 kilo ohms. Below it gets hard, and above it gets hard. Then you can use the impedance adapters. They widen the impedance measurement range of the Bode 100, and we recommend to use them from 20 milliohms to approximately 600 kilo ohms. The 20 milliohms come from the fact that these adapters are not Kelvin connections, so it's 2-wire connection, and you will always have contact resistance in the area of several milliohms, so it doesn't make sense to go below 20 milliohms. And the external bridge or external coupler method, you can design your own bridge that is sensitive to a special application. Then the indirect measurement method, and the most well-known or the most known type is the shunt-through method. That's actually S21 transmission measurement in the 50 ohm system, but the device on the test is put like a shunt in the system, and this setup is most sensitive for very low impedance values. It's recommended for, let's say, from 1 milliohm to approximately 10 ohms. So here we can really measure 1, 2, 3, or 5 milliohms. And the Bode will show the S21 transmission parameter, and you have to calculate the impedance from that. And the equation is shown here on the right-hand side, so it's 25 times S21 over 1 minus S21. However, S21 is a complex value, and also the impedance will be a complex value, so it seems to be very easy, but you need some math for it. We have done an Excel spreadsheet. In case you're interested in this measurement method, you can get an Excel spreadsheet from us.
And then you just export the trace data from the Bode 100 into this Excel spreadsheet, and it calculates the impedance for you.
Same for the series through. This method is more sensitive for very high impedance values. And the voltage current gain, yeah, here you can use voltage probes or current probes. You can also measure active devices with that, so input impedance or output impedance, things like that. The impedance range is summarized over frequency in this chart. So we have in the middle this brownish part, that's the one-part reflection, that's the constant over frequency, and yeah, here we have this half an ohm to nearly 10 kilo ohm range that we recommend to use it in. And on the lower side we have the green area, that's the shunt-through method. And here on the left-hand side you see there is a statement that says use common mode suppression. And the reason is that in this measurement method there can be an error that is introduced by the
ground loop,
by the cable braid, and you should use a common mode choke.
Yeah, and if you're looking for a common mode choke, there is one from Picotest, J2102. That's the one we are using.
And on the right hand side, above 100-200 kilohertz, I made a blue line, so that's the 1 nanohenry line. You can see that 1 nanohenry adds significant impedance at 1 megahertz already. So I would say you have to take a lot of care if you want to measure inductance below 1 nanohenry. So I don't recommend doing it. You can try, but it will take a lot of effort.
Possibly Steve is able to do it.
Steve does it.
Yes,
you need to take a lot of care. I don't do it. Then on the upper side, for the series through, I did choose the 0.5 picofarad as a limit, which I recommend because 500 femtofarads is not a lot, and if you build a test setup somehow with the surface, with a test board with some PCB, you will very quickly end up with 0.5 picofarads capacitance between two electrodes. And the impedance adapter is somehow in between of everything, so that's the general purpose impedance measurement method that we will also use now during the webinar, since it has the advantage that the device and the test can be quickly removed and added because it's a test fixture with clamping. Yeah, Bernhard, and I do now hand over to you.
Well, thanks a lot, Florian. So, why is it important to measure capacitors? Everything is in the data sheet, we think. No, it's not. So, first of all, the reason why we need to measure capacitors is because a capacitor is never just a capacitor. Further on, capacitor ESR influences a lot of things when we are developing power supplies. So, for example, the phase margin that we achieve for a power supply depends on the ESR. And ESR also influences the output ripple at the switching frequency of a switched mode power supply. And since the ESR changes over frequency, it might be interesting to know exactly how the ESR behaves over the entire frequency range, so that we know what ESR we have at a certain frequency that is important for us during the design. Well, and finally, capacitors become inductors above the resonance frequency, and so it should be also known if the capacitor we are planning to use is really a capacitor at the frequency, it still has to be a capacitor. So these are all reasons why we want to test capacitors. Now, what does the data sheet tell us? I have looked up a data sheet for a 220 microfarad aluminum capacitor, and if I have a look, and the data sheet tells me a lot about the dimensions, but it doesn't, and how many pieces are in one batch that I need to buy, but I get only very little information on the capacitor itself. I get how many microfarad it has and what tolerance, and I get a tangent delta reading for one frequency, in this case 120 Hertz at 20 degrees, and then I can calculate the ESR from that. But that's it. That's the information I have. Maybe if I would call the manufacturer and ask for more detailed data sheet, I might get one, but that's not always sure. So let's measure this thing and let's see what the measurement tells us. So this is what the measurement tells us. First of all, we can look at the impedance curve, and we see immediately that we have a drop with a 20 dB per decade, and this is where we have the capacitor. So as Florian said, it's a short circuit for high frequencies, but unfortunately, we come here into an area where we can see the ESR, and then the capacitor becomes an inductance, and so it goes up again. So at high frequencies, it's no longer a short circuit. If we look at the phase, we also see this behavior. So we have a 90 degree in the beginning, so it's a perfect capacitor, but very soon it rolls off, and it comes closer towards 0 degree. Here it's resistive, that's the resonance point, and then it goes further up, and it becomes an inductor. And here it's already a perfect inductor with 90 degree phase shift. If we look at the ESR, we also see that the ESR at 120 Hertz is about 233 milliamps, 200 milliamps, and then it goes down, and it comes up again. So this is also something to be taken into consideration when we want to have circuits which are sensitive to ESR changes. And finally, if we look at the capacity, the capacitance of this capacitor is 217 microfarads, should be 220, but since it's plus minus 20%, we can be happy that we got such a nice sample. So now let's measure a capacitor. In fact, we have prepared several capacitors, and we have prepared our impedance adapter. But before we have to do the measurements, we have to do a calibration. And since we get now and then questions about how to perform the calibration correctly, we have included it in this seminar. So we do an open calibration where we don't plug anything into this adapter. Then we plug in the short side of this board that comes with the adapter to make the short calibration. And finally, we put in the load and we make a load calibration. And our recommendation is that you keep the device under test or this calibration board inside and then check if you really get a 100 ohm reading and a flat phase, because then you know that you have done the calibration correctly.
And you can also remove and place again to check if you had good contact during calibration.
Very good point. So the second question we always get in relation to calibration is, what is the difference between user calibration and probe calibration? Because most of the systems in the market, they are just offering probe calibration, which is a thing where you use linear interpolation. But let me start with the user calibration. In the user calibration, you first define a start and a stop frequency. You define a number of points. And then when you perform the calibration, a set of calibration factors is defined for every frequency point. So the open, short, and load calibration factor is determined for every single frequency point that you have in your measurement. The advantage is, if there are some non-linearities in your measurement setup, or you have some narrowband probes that have some very narrowband behavior, then this is fully compensated using the user calibration. However, there's a disadvantage. If you have to change your start frequency or stop frequency, or even just the number of points, the calibration values are no longer at exactly the point that they were before, and thus we throw them away. Because we say in the user calibration, you have a calibration set of calibration factors for every point. The other possibility is to use the probe calibration. This is a full range calibration. So when you perform a probe calibration independent from your settings, we always perform a calibration over the entire frequency range using factory defined points for the calibration. And then you define your start and stop frequency and you define your number of points. And then we calculate the sets of correction factors for each frequency point by linear interpolation. The advantage is that if I change start or stop frequency or the number of points, we can keep the calibration. There is no need to recalibrate. How do we do this in the real life? 99% of the time we're just using the probe calibration because it's very accurate, and as long as there are no non-linearities in the measurement setup, you are not running into any trouble. If you then see suddenly strange ripples, where you might think, okay, this everywhere where there is a spike downwards is a point where this curve seems right, and in between there is something wrong, then this can be caused by the fact that not every point has its own calibration point or correction factor, and then you can do the user calibration in addition. If there's a user calibration and a probe calibration available at the same time, always the user calibration is used. But you can switch it off independently. Okay, so now let's do a calibration and then measure a capacitor.
Yeah.
So I bring on the camera. Next one. So, and here we have our adapter, and I will start the Bode software. We already have our old measurement in. Let's do something totally from scratch. So I select the impedance adapter mode, and if I now would like to perform a measurement, it would tell me immediately that I have to do a user calibration or a probe calibration. So I choose to do a probe calibration, and I start with open. So Florian, can you please?
I don't need to do anything with open, in fact.
Ah, yeah, but can you please? I need to bring in the camera. That's what I wanted to say. So we do the open calibration. And now can you please plug in the board?
Yes.
With the correct side, the shorted side, yeah. And finally, please plug in the load side.
Load is plugged in.
Okay. Okay. And now we can already see a flat line at 100 ohms. So let's also check the phase. I will go bigger and to do diagrams. And now we see that we have a flat line at 0 degree and a flat line at 100 ohms. So it looks like we've done a good calibration, but let's do the test that you said, remove it and plug it in again. Okay, looks good. Excellent. So we have done a correct calibration. And as a next step, please put in a capacitor.
So what would you like to have?
Yeah, let's start with an aluminum cap or electrolytic cap.
For 10 microfarad aluminum cap, 400 volts. So it's quite high voltage but low capacitance.
Okay, so if we switch here to double logarithmic reading, we can see that this capacitor starts with 20 dB per decade, then it flattens down where we have where it's nearly resistive, and then at the end we get already an inductance again, so it's starting to climb with 20 dB per decade. If you look at the phase, we see the same starts at -90, so capacitor, then becomes close to resistive, it flattens down, and then crosses over to +90 degree, and then it's an inductance. If we switch here from phase to the capacitance, we can see the capacitance and we can also measure it. Let's say we want to measure it at 1K. And we see that the capacitance is at 1K, it's 8.7 microfarads. If you would look at 100, it's bigger. It's 8.9 microfarads. This capacitor has plus minus 20%. So this is definitely within the range. Now what we can do is we can also have a look at the ESR. And this is the ESR, and let's store this data to memory. And let's use a different capacitor, but before we do so, we will go back to magnitudes. And now please pull out the capacitor a little bit from the fixture.
Can you select data and memory?
Yes, I will do so.
See the difference.
Data and memory.
So I'm pulling now out the capacitor from the fixture by...
I will put the camera on. So, now do it.
I just pull it out by approximately 5 millimeters.
And you immediately can see the change at the upper frequency. The inductance has moved. In fact, the resonance frequency has moved. We can see this down here. If I... Oops.
You scrolled in the data and memory.
Data and memory.
Format is now magnitude. You want phase or something like that.
I want CS. So here you can see it. Now you can see how the resonance frequency has shifted, just to the fact that we have 5 millimeters more of leads. So if you, for example, plan to put in this capacitor due to space requirements lying, you will have a longer leads, and therefore you already have a different performance, different resonance frequency. But even more interesting is the different ESR and different behavior for different capacitors. So let's use again a 10 microfarad capacitor, but this time a foil capacitor.
Okay.
Camera again. Okay.
I remove the aluminum and place in a metal foil.
So you can see it has a much lower ESR. It's also working up to a higher frequency. If we look at the CS, I possibly have to zoom a little bit. So now you can see we have a very good 10 microfarad reading. So this is a very accurate capacitor, and it's very flat. And here you see also a nicer performance. So I will choose a new memory, and I'll give it also a name, foil capacitor. And I can store the data again. Do the same on the second trace.
Okay.
And now we can also switch to ESR if we want to compare here. And we can see the difference in ESR between the aluminum capacitor and the foil capacitor. Now let's use, as a last test, let's use a ceramic capacitor.
Okay, a ceramic one. Same capacitance, but a lot smaller.
I need to put it in camera, so yeah. Okay, so what we can see here immediately is that the ESR is even lower. So here we are at 10 milliohms, and now we are below 10 milliohms. We are in the range of somewhere 4 to 5 milliohms, and here you already see quite some noise. And the reason for this is, as I told you, we do not recommend to use the impedance adapter for really low ESRs. So there are different methods to be used, like the shunt-through method introduced by Florian. And so you can see two different capacitors with different material result in totally different ESRs.
Yeah. I think as the last one, I would like to measure the blue one that you have shown before, because I would like to use the data afterwards.
Okay, good. And you want to have a magnitude curve, I assume?
Yes. So that's now 220 micro aluminum, and I would like to, if you could please export the data to the desktop.
Data,
Yeah,
you just need this one.
Export the CSV file.
Export trace data.
And I call it
Aluminium. Okay, so done.
Yes.
So now I think you need to tell the people what you want to do with this, but before that, we have a detailed measurement example of measuring capacitor ESR on our web page, so feel free to visit our application notes section, download it and have a look in more detail.
Yeah, and as we said in the beginning, we would be happy to answer questions, so please post them to the chat. We will address them anonymously, so feel free to post them to Bernhard. Yeah, and what I wanted to say, I mentioned in the beginning that it can be hard to fit all the data, all the model parameters to the measurement data, especially if you're using higher order models. And we have worked on a little tool that's not yet officially released. We plan to integrate it to the Bode Analyzer Suite in future. However, until then, we have a little preview tool that we can distribute on request. I would like to demonstrate that now. So this is the tool, and I will now load the CSV file that I have created before. So it was on the desktop, and it was called aluminum CSV. I open that, and I get the impedance, magnitude, and phase curve from the measurements that we have done with the Bode 100. So I select now capacitor, and let's assume that I would like to have the capacitor 3 model here. Then I can press start curve fitting, and then the tool will try to fit the parameters, it varies the parameters, until they fit to the measurement data. However, in this case, you see the blue data, blue trace, that's from the simulation, from the parameters that the tool calculated. You can see that the right hand, the capacitor 3 model, that's not really applicable to that measurement. So it only contributes for the series, for the parallel losses in the electrolyte, and they are not dominant here. Here the series losses are dominant, so I'm choosing capacitor 2 model now. I start curve fitting, and I get a much better result. And here on the lower hand side, you can see the R, the L, and the C. The tool has calculated for me. So it's about 3.8, so that's 4 nanohenries of inductance and 113 milliohms of series resistance and 217 microfarads. So in case you're interested in using this tool, please send us an email to info@omicron-lab.com, and we will provide you a demo version of this tool, a free.
Well, in fact, it works, but we don't give you any warranty. Okay, there's a question, and the question is there a way to export component measurements as a touchstone file instead of CSV?
Yes, in fact, there is a converter. So if you go to the Omicron Lab web page and you say download Bode 100, then there is under other, there is a Bode file converter, and the Bode file converter will convert Bode files to touchstone.
So in this case, you do not have to export CSV, you just store the file as a Bode file. So I'll just show you in the Bode 100. So you go to File and say Save, and you just save this file, and then you start the touchstone converter and open this file inside the touchstone converter, and it will create a touchstone file for you.
Yeah, you can choose which trace you would like to have and which parameter you want to export to.
Yeah, and I think there's a short explanation with the file how it works.
Yes. If you, yeah. Okay.
Right. Very good. Thanks for the question. So let's go back to the presentation.
So yeah, if you put in the values the tool did spit out into, for example, LT-spice, then the result will look a lot similar, more similar to the measurements than before.
Yeah, and there's another thing to be taken into consideration when we talk about capacitors. Capacitors also can change over voltage. And this is also an important topic. We once had a case with a customer. He had a very nice calculation sheet from a manufacturer of regulators and regulated chips, in fact, and he calculated everything correctly, and then he measured with the Bode 100 and he got totally different results. And it ended up that he sent me from the Far East some capacitors to measure, and in the end of the day, the problem was that the capacitor was no longer 100 microfarads. At the 5 volts he had, it was only 40 microfarads. And when we entered the new value into the calculation sheet provided by the chip manufacturer, suddenly the results of the simulation and the results measured with the Bode 100 matched. And so that's an important thing to take into consideration. For many people this is well known, but still we are making the point because it happens now and then that people forget about it. And to do this measurement, we are using a picotest device. It's the J2138 DC bias injector. Was developed by Steve Sandler, a very good friend and business partner of ours, who's done a lot of injectors that help us to do measurements on power supplies with the Bode 100. And with this injector, you can add a DC voltage to the AC output of the Bode 100 and then feed it into a capacitor. And this application note shows exactly how to do it. And here are some extracts from the results. So this is a normalized diagram. So you can see how the capacitance deviates from the nominal capacitance over the voltage. So this is the nominal voltage of the capacitor. Let's say it's 10 volts. And let's say we have 100 microfarads, and this would say us that this X7R capacitor has around 40 microfarads at 4 volts DC. 4 volts DC, yes. So that's important to take this also into consideration, but it's not part of this webinar. Okay, so let's move on for inductors. Why should we measure inductors? Yes, same answer as before, because an inductor is never just an inductor. So there is, usually when you look at the data sheet, you get a DC resistance, but this is not the resistance the inductor has at AC, because there's skin effects and eddy currents that influence the resistance at higher frequencies. Further on, inductors have resonance frequencies, quite sometimes more than one, and due to the magnetic cores used for inductors, we also have core losses. And these are all things we're interested in because losses inside the inductor result in heat in our switched mode power supply in the end of the day. So what does the data sheet tell us on an inductor? We have picked a high quality inductor, which is a 33 microhenry shielded power inductor. And if we have a look at the data sheet, we can see the value and the tolerance. So I've written it out a little bit bigger. We also see the DC resistance, but we do not, and we see the resonance frequency, which is a typical resonance frequency, but we do not get any input on the AC resistance or impedance. So what do the measurements tell us? If we measure this inductor, we first of all see that it's a high quality inductor because it has a very pointed resonance. It goes up with 20 dB per decade very nicely. And if we see that the resonance frequency here is at 13 megahertz. So this is just because it says 11 megahertz as a typical value. If it's higher up, it's in fact better for the component because we want to have this device to be inductive as long as possible. The same thing is we have here. If you look at the phase, we see the crossover point for the phase is at the same position, so it's the resonance frequency. For sure, an inductor cannot start at 90-degree phase shift because it's the losses from the winding. And if we look at the ESR, we immediately see that the ESR changes over frequency, and that's quite interesting because the ESR means loss inside the inductor. And if we, for example, would have a switching frequency of 300 kilohertz, then we would see that the loss is of this inductor is already above 1 ohm. And so this already can result in some heat buildup inside this inductor, depending on the current we are using it for.
And the low frequency value fits very well to the data sheet. That's here 40 milliohms.
Yeah. So it's perfect. Yeah, and finally, if we look at the inductance itself, we see that it has 33.019 microhenry. So that's perfectly nice. Measured at 290 hertz, and if I look even at 100 kilohertz, it still has 30 microhenry. So it's way well within the range defined. So it's a high quality component. Would not have expected anything else from this manufacturer in any way. So that's before we look at the flyback. Do we have time to measure an inductor, or shall we go forward to the flyback immediately?
I think we can go forward since this is an inductor itself. So.
Yeah, okay.
We can measure the primary inductance.
Okay.
Yeah. So sometimes you get the question, is it possible to measure the leakage inductance of a flyback transformer with the Bode 100? And certainly the answer is yes, of course it's possible. But first, let's have a quick look on what is the leakage inductance. If you're designing flyback transformers, you will for sure exactly and way better know what is leakage inductance than we do. However, we have tried to summarize it here on that page. We know that not all of the flux that is generated by the primary side is really contributing to the secondary side. So some flux is lost, and also some of the flux is contributing to losses inside the core. And this can be modeled by using an additional inductance, the so-called leakage inductance, that is not part of the coupled inductor in the model. So let's assume we want to switch off the primary current very quickly. Well, then it's getting hard if magnetic energy is stored in the leakage inductor. Since this inductor is in series, it doesn't like to be switched off, so the current doesn't want to be switched off, and it will create a voltage spike. And that's exactly the problem of flyback converters if the transformer has too much leakage inductance. So there is an interest in measuring the leakage inductance. And we will measure the leakage inductance, and that's normally done by making a test with all the secondary windings short circuit. So in this case, we have a flyback transformer that has one primary winding, one bias winding, and two secondary windings. And on one of the devices, I have shorted all the other windings except the primary winding. So let's do that.
Yep. Yeah. So maybe you show this to the people in the camera.
So these are the two devices that I have. So one of them is shorted on secondary and the other not. And we'll now first measure the primary side inductance by using the transformer that has open ends on secondary. I now remove the capacitor and I place in the transformer primary side.
So again, we can see the impedance rising 20 dB, and
we calculate inductance in the second phase.
Yes.
And only data, not memory. So the primary side inductance is around 130 microhenries. So quite high inductance. And maybe you can store that to the memory.
Yep, just a second. Do the same over here. Okay, done.
Okay, and I'll remove the open winding and place the short circuit inductor.
I still have some capacitors in here, so now it's gone.
Okay, so in the upper chart we see that the inductance has reduced now since we short circuit the secondary side. The only thing that is left is the leakage inductance, and in the lower display we get the leakage inductance value. Maybe you can remove the memory such that you can see better. So you can see at frequencies above 10 kHz, the leakage inductance is very small. Let's measure it at 100 kHz, for example.
Switching frequency?
Yeah, maybe. So it's 600 nanohenry, so 0.6 microhenry is the leakage inductance. And at 1 megahertz, at 10 megahertz, now we can see it better in logarithmic Y scale. So at 10 megahertz, it will then be approximately 400. Oh yeah, 1 megahertz is 430 nanohenries, so 0.43 microhenries. Yeah, that's quite easy, I think. So in case there are no questions, we will now move on with our presentation.
Yeah. So far so good. No questions. So go back to the presentation.
Yeah, so what we did see is that the leakage inductance strongly depends on frequency. So it's not constant over frequency. So if, in case you want, it's same with ESR, if you want to know leakage inductance, you need to tell at what frequency. And the next example that we have prepared for a live measurement is an LC filter, based on the fact that the LC filters are used generally in all power converters, in all switching converters. We have done a very simple simulation in LC SPICE with some ideal components. So 8.2 microhenry inductor and 220 microfarad capacitor and different load resistors, and we get the transfer function of the low-pass filter that has a pass band and a resonance with a double pole and a stop band with minus 40 dB per decade falling slope, and the phase turns to minus 180 degrees. So we built the same thing with real components, and we will measure that transfer function now by comparing input and output voltage over frequency. And this is done by using the Bode 100 in the frequency suite mode. And I will now connect it, and Bernhard will set up the Bode analyzer suite.
After I've shown the people how you connect it.
The output of the Bode goes to the input of the filter. The high frequency design layout on, what's it called?
No idea. Lochrasterplatte, I have no idea what that's in English.
Okay. So now
okay, so it's connected. And we go to the Bode 100. We switch to the sweep mode. And since this measurement uses an external reference, we switch to external reference. So we pick up the input signal that's going into the LC filter with channel 1. And at the output, we have channel 2. And for sure, we have to use the logarithmic scale and maybe also start at the lower frequency. And now I hand over to Florian.
Thank you very much, Bernhard. So we already see the pass band at the left-hand side, and then we have the resonance frequency of the filter, and then we have the stop band, and then we have some high-frequency stuff going on here.
High-frequency stuff, yeah.
So let's also display the phase. I select measurement, gain here, and format phase. So that's the phase. Does not really go to minus 180 as we said before. So what happens here? We have the measurement that looks like that, and we have the simulation that looks a little bit different. So the stop band is actually totally different. We have phase doesn't go to minus 180, it stops at minus 100, something like that. And the slope is not minus 40 dB per decade, it's approximately minus 20. And there is a second resonance at 30 megahertz. And everything is caused by the parasitics of these components, and probably also a little bit of my, I call it the layout, RF layout. Yeah, so I tried to model that in LT-SPICE by using the equivalent circuits of the parasitics, of the components actually, and the result did look a lot better compared to the measurement. However, there is still a little difference that could further be improved by using more complex or more sophisticated equivalent circuits. And something else that I would like to show to you, because you very often see that, and I'm probably sure that quite sure that you are aware of that. If you want to reduce the output ripple of a switching converter that uses this output filter, for example, then we could add a smaller ceramic capacitor, and I will show you what this does to the transfer function. Let's place on the camera here, and I do now add a 2 × 10 microcapacitor, ceramic capacitor. So the total capacitance does not really change, but at higher frequencies, the curve changes dramatically. So let's assume we have a switching frequency of 300 kilohertz in this converter. Then the attenuation of this filter did improve by more than 20 dB. So you would get a lot less output ripple, and that's due to the fact that the ESR capacitor, that the ESR of the ceramic capacitor at that frequency is much lower than the one of the aluminum cap.
Yeah, now they are in parallel to the aluminum cap, so the smaller capacitor is dominant.
Yeah.
Well, and to summarize our webinar, component parasitics are important to understand the real-life behavior of circuits. And models considering parasitics allow a much better simulation than just using standard capacitors. So by using curve fitting, for example, you can use your measurements you do with the Bode 100 and create nice SPICE models. And measuring components can tell us a lot more than we can get from the datasheet. So these are the key findings we presented for this webinar, and we are now ready for your questions. Again, if you want to have the conversion tool, so the tool to convert into touchstone parameters, or if you want to have the curve fitting tool, or if you want to have the Excel sheet to calculate from gain into impedance when you use the shunt through or the series through method, then please send us an email at info@omicron-labs.com. However, I've seen there is just a question has arrived. I will read it to you, Florian, which means that you need to answer it.
Yes.
What is the influence of value of reference resistor? You also use value 50 ohms, but you don't have it set up.
Yes.
Ah, okay.
Okay, so the value you see here in the Bode suite, reference resistance, this value is used to calculate the reflection factor. So if you're doing an impedance measurement and you want to display the reflection factor, so reflection coefficient or voltage standing wave ratio or things like that, then we need to know in which system is it a 50 ohm characteristic impedance, 75, 100, 200, whatever, and then you have to put in this value. If you're only measuring impedance or gain, this value is not important to you.
So it's a reflection of VSWR. So we can do a quick thing here. We can switch to, okay, we possibly see something stupid, but doesn't matter. We switch to reflection, and we switch to, for example, the Smith chart. Now you see the center of the Smith chart is at 50 ohms, and if I would change it to 100, then the center of the Smith chart goes to 100. So this is the reference value for calculating the reflection or the VSWR, and that's all. And we already plan for future release of the Bode 100 to make this more clear. So this is not the resistance that is used during calibration. If you do a full board calibration for impedance, then the reference resistance is put in here, and it's either 50 ohms if you are in the 50 ohm domain, or if you use our impedance adapter by design, it's 100 ohms, but you can enter values here if you don't have a 50 or 100 ohm resistor at hand for the calibration. So I hope that this answers the question. Okay.
Nice feedback. Thank you very much.
Nice feedback. Thank you. So.
Okay, we'll stop the recording now, I think.
Yeah, still feel free to ask questions, and they are no longer recorded, so maybe even easier to ask questions.
So thank you very much for watching.
Yeah, thanks for attending the webinar. Have a nice day.